Hello, this is Mr. Pruitt, and today I am talking about forces. This is part one of a series on forces for my high school physics class. I will be talking about basic force concepts and definitions. Alright, so what's a force? Well, a force is just a push or a pull. And the man that is pushing the woman on the skateboard is an example of a force, and the young man that is pulling his little sister on the sled is also an example of a force. Forces are also considered to be vectors. That means they have both a magnitude. Remember that a magnitude is just a number. Sometimes when we're referring to this with forces, it's referred to as the strength of the force. And then they also have a direction. So the direction the man is pushing the woman is the direction of that force. The direction that the young man is pulling his little sister is the direction of that force. And then you need to remember that forces are the basic cause of acceleration. As long as the force is being applied, acceleration is going to be occurring. So in the case of this man that's pushing the woman on the skateboard, as long as he continues to push her, she will continue to go faster. And the same thing with the young man that's pulling his little sister. We have two ways that we're going to talk about classifying forces. The first way is we're going to just talk about how the force is applied. The first type would be what we call contact forces. And those are just forces that are applied by physical contact. So if you're looking at our little box guy down here, and he's got a rope and he's pulling the rows along with him, he's in contact with the rope, causes tension in the rope. The tension in the rope pulls the rows along, and all of these places where there's being force applied, uh, there's actual physical contact between those objects. The other type is what we call a field force, and field forces are forces that can affect an object at a distance. The man falling down the stairs here is obviously being affected by gravity. Gravity is a good example of a field force. Uh, Gravity doesn't actually have to be touching you, you just have to be within its field and you are affected by it. Other examples of field forces would be magnets. You know, when you get them close enough together, they either push apart uh, or they pull together without any help from you. Or electromagnetic type forces would also be a good example of field forces. Another way to classify forces, and probably a more important way, is to classify them as either balanced or unbalanced. Okay, balanced forces are basically force pairs that are of equal magnitude, but they're in opposite directions. So when I look at this bowl sitting on this table, the weight of the bowl is directed downward, but the table pushes upward on the bowl as well in an equal amount. And I can tell this because if the weight of the bowl was greater than the table, it would be falling through the table or breaking the table at this point. And uh, if the force of the table pushing up on the bowl were greater, then my bowl would actually be floating around off the table, and neither one of those is happening, so they must be balanced or in equilibrium. Unbalanced forces, which are a little bit more interesting, these are the types of forces that cause acceleration, are force pairs that are of unequal magnitude in opposite directions. So if you've ever played tug of war and you've ever been pulled through the mud, uh, just think that the other team has an unequal amount of force in their direction and they're pulling you forward and through the mud. Uh, or if you have two forces in opposite directions and one of them is stronger than the other, then we would say that they are of unequal magnitude in opposite directions, and those forces would be unbalanced. That would be causing the unbalanced force would be causing it to accelerate in the direction of the stronger or greater force. Another term you need to be familiar with is net force. Net force is the sum of all the forces on an object. Um, it's really easy to find net force. Basically, what we do is we subtract all the opposite force pairs from each other, and then we add up the totals. So in the example over here, this is an example of balanced forces. If you take the two vertical forces and you subtract them from each other, 50 minus 50, you get 0. And then you take the right and left forces and you subtract them, 30 minus 30, you also get 0. We sum those up, 0 plus 0 is still 0. And we know that the net force on this object is 0. if this force right here were greater, let's say that it was 40 newtons instead of 30, then we would sum it up like this. We would say 50 minus 50 is 0, 40 minus 30 is 10, and that would give us a net force of 10 newtons to the right. All right. When the net force is equal to 0, we say that those forces are balanced or that they're in equilibrium, and sometimes those types of forces are called static forces. And when they're not equal to 0, we say that those forces are unbalanced, or that those are dynamic forces because they're getting acceleration. Before I finish up today, I really need to make a note to you guys on the difference between mass and weight. These two ideas are going to come up a lot during the next 4 to 8 weeks of the class, and I need to really understand what the difference is between these. And the reason that there's even confusion with these weights is because they're used fairly interchangeably by most people, but they're not the same thing, and it creates somewhat of a misconception. Okay, you need to remember that mass is the amount of matter that makes up an object. Okay, so when I look at this astronaut here, all of the parts that make up her, plus all of her spacesuit and her pack, would be her mass. And in this case, that mass is probably pretty close to 120 kilograms. Weight, which is sometimes also called the force of gravity, is the amount that gravity pulls on the object's mass. So when we're on Earth, the weight, which would be expressed in newtons, would be 9.8 times the mass. Okay? Or if you were in space, it would be like in this situation, there is gravity in space. But let's say that in this situation that it's more like half a meter per second instead of 9.8 meters per second. And so as we're here, the actual weight went down, although her mass, the amount of matter that makes up her spacesuit and her, should be relatively unchanged. Anyway, I hope this was helpful for you. Please bring these notes to class tomorrow, and we'll start from here. Thank you. Bye.